tutorial, I'm going to go over the kind of real basics, or what I think of as the basics of Bayesian inference, which is really just probability theory. And I've also got a few exercises for you to do if you're a beginner and want to try and get the hang of things. So if you go to the repository for this conference and go to the inference subdirect, probability questions or exercises, I forget which one it is, but there's a PDF there of the questions. Okay. So what we're really doing when we're using Bayesian inference or Bayesian statistics or Bayesian anything, the fundamental thing we're looking at is propositions. And propositions is like a philosophical word, but it just means like a sentence that's either true or false. And so here are some examples of propositions. Proposition might label A would be about Hillary Clinton being the president at some point on that particular date. Proposition might be about the value of a cosmological parameter, like proposition C there about omega lambda. And propositions can be true or false, and even ones that are like axiomatic, like my proposition D here, is still a proposition. And what we're trying to do is, with using Bayesian inference, is we're trying to reason about whether propositions are plausible or not. So we're assuming that all of these are either true or false, and we just don't know whether they're true or false. But based on the information we have, we might think, oh, it's very likely that this is true and that that's false.
Many of the problems that people in this room have are about estimating not whether or not I've had 500 milligrams of caffeine, but how many milligrams of caffeine I've had.
Yeah.
You can't estimate like a continuous parameter. Are you going to connect measuring continuous parameters to this?
I'm not going to do the formal thing of going to the continuum. I'm not going to do that formally, but I am going to connect propositions to parameter estimation, if that makes sense.
Fine.
Yeah.
I will re-ask my question if it's unclear.
Okay, cool. So one of the things you can do with propositions is that you can combine them to make new ones. And there are three operations you can, there may be more, I'm not sure, that you can use to make new propositions out of old ones. And I'm going to write them as and. I'm going to write with a wedge, or is with a V, and not is with this funny looking symbol. And the reason I like these, there are other different sets of symbols that people use, but when you use this one, especially the not, I feel like you're writing some advanced philosophy, so it's kind of fun to do. So if you had two propositions A and B, that could be this A and this B, but could be anything, then A and B, that's defined as true if both A and B are true, and if either A or B is false, then A and B is false. So this is just the standard logical stuff that you're used to. You can use or. C or A will be true if either C or A is true, and this is not exclusive or, it's the standard or. The negation, so not D, is true if D is false, and you can build up more complicated things like not, or the negation of A or C and D, things like that. And the rules for how these kind of combinations work, those are called Boolean algebra, and if you want to learn that, you can go on the Wikipedia article, and there's heaps of stuff there, and it can get fairly complex. Okay. Just as a matter of notation, I just said I was going to use and with a wedge, but sometimes it's just written with a comma. Actually, it's more common that you have a comma in when you start dealing with probabilities. So in science, it's quite rare that we know for certain whether something is true. Whatever we're studying, we don't know, we're not sure, and we're trying to get more information. So what we want to do, or what we're often thinking about, is how plausible certain propositions are. So we might say, I'm very certain that the mass of the sun is greater than 10 to the 30 kilograms, or I'm not very certain that that there was once life on Mars or something. And so what we're trying to do is we're trying to take propositions and assign real numbers to them. So every proposition we might be thinking of has a real number associated with it that describes how certain we are that it's true. And how plausible a proposition is depends on what you know. So it's a function of two propositions. The first one is the one you want to know the plausibility of, and the second one is the stuff that you know happens to be true that you're using in order to inform that plausibility. And so you can write this down as the plausibility of A given B. So you read this bar as given, and that would be a number that tells you how confident you are that A is true, and to inform that you're using the fact that B is known to be true. You can do that with any two propositions, so you could have not D given C or D, and whatever, any two propositions. So I've deliberately said that these aren't probabilities yet, I've just called them plausibilities. It remains to be proven that if you want to do this, that these P's actually have to be probabilities. And there are a number of fairly famous papers trying to prove that. So some obvious properties of what plausibility should do. It should do something like this. If you have a proposition A and it has a certain plausibility, then if you put another proposition onto it with OR, then the probability can't go down, it has to go up. It has to be more plausible. A or B is always more plausible than A on its own, because you've given another option. It could be that A is false, but B comes in to save it. So that's one property that these P's need to satisfy. And another property is, I think this is called associativity. And that is that with some of these Boolean operators, there's a symmetry. So that if you do A or B or C, that means the same thing as A or B or C. And so those plausibilities of those two things, because they're the same proposition, they have to be the same plausibility. So in the previous slide I said that these plausibilities depend on two propositions, but I've left off anything after the given bar in this slide. So what I've done here is I've assumed that everything on this slide just has a common given D, or given something else on the right hand side of every bar that's kind of implicit in all of these. Now there's a really wonderful paper that I'm trying to read, and it says in the introduction, it says we present a simple and clear proof of the fact that this and a couple of other symmetries imply that these have to be probability. And this simple and clear paper, I've been looking at it for about 2 months, and it just looks like such a wise and awesome paper, but I haven't quite gotten it to be clear and simple to me yet. Yes? Yeah. Sorry? Yeah. What's known so in the second one here, given C or D is true, that would mean that you just know that either C or D is true. You know that the proposition C or D is true. You know that either one of C or D is true. They can't both be false. And that's all you're using.
In practice, there's some suspension of disbelief, right? So much that you know that the stuff on the right hand side is true, but you can temporarily assume it.
Yes, yeah. A lot of the time when you condition on something, you say, given this, you're pretending to know it. And we'll see how that works in some of the examples.
Sometimes people describe these things using Venn diagrams. This is the only possible use of Venn diagrams. If you draw, it's a nice exercise to draw the Venn diagrams for the thing where there's the space of all possible universes, and then there's the space of universes where A is true, and B is true, and C is true, and D is true. And then all of these expressions become areas in this Venn diagram.
They do. It's very closely related to measure theory and things like that. And as soon as I say the word measure theory, I'm going beyond things I should be talking about, so I should probably move on. Okay.
saying that the proof that you get probabilities here is challenging, and I agree. But I thought the presentation in James is really good. I don't love the book by James, but I love the first two chapters where it demonstrates that if you just want to reason consistently about these things, you get probabilities.
Yeah. So the classic references for this proof that wanting this kind of consistency with Boolean algebra and quantifying plausibility, you have to use probability. The classic papers are by Cox, 1946, I think. Jaynes, the book by Jaynes, Probability Theory, the Logic of Science.
Yeah, I'll tweet the reference to the book by Jaynes.
Okay.
If people want to read more, I think it's
And the simple and clear paper that I'm trying to work through is by Knuth and Skilling, and it's in the journal Axioms. Sorry? Okay. So I've hopefully not said the word probability by accident instead of plausibility too many times, but they turn out to be exactly the same thing. So if you want to have certain properties that make obvious sense, then it turns out that if you want to quantify plausibility, you have to use probabilities. Yep. Yes?
Can you please give an example where something is plausibility but not probability?
I don't think such a thing exists.
So why those are two different things?
They're two different things up until I say it's been proven that they're actually the same thing. But they're really the same thing.
Prove them if the number of assumptions I make that the plausibility of A should be greater than equal to 0 and the two others who wrote there.
Yeah.
It's the definition of probability.
It is. Which did I define?
The constraints, they are actually your definition.
This one is probability theory implies this, but this on its own doesn't imply probability theory.
Oh,
and
okay.
same with that one. So I think it's these two on their own. They give you measure theory, and then there's something else gives you the
When you say
product rule.
You mean the usual approach, like you have a measure, like a probability space, the triple, right?
Sorry.
When you say probability, you want to prove plausibility is the same as probability.
Yeah.
So by probability you mean the usual formal mathematical definition of a probability space, its measure, and
That's getting a bit too advanced, I think. So I don't actually understand formal mathematical definitions.
yeah.
Because plausibility is something which people thought was just like some subjective thing.
It's like a feeling that you have. Yeah.
And then probability is this formal mathematical theory. And then when people tried to ask, well, could there be a quantitative theory of plausibility? Bam, it becomes probability.
Yeah. So there are some alternatives to probability theory that people have come up with. There's one where instead of giving every proposition a probability, you give it like two numbers. You give it a lower bound and an upper bound. You can think of it like a lower probability and an upper probability. The problem with that theory is that it doesn't give you this. Because as soon as you say that these two, as soon as you say that instead of just one number being associated with A and with A or B, there's two numbers, you can't say that this one's greater than that one. And that's like, in the presence of uncertainty, that's like the minimal thing that you can say. If I'm putting an or something else, probability has to go up, or at least stay the same.
So some of your propositions early on were about properties of the universe, parameters of model universes.
Yeah.
And so is this point mapping plausibility onto probability? Is this the point where the frequentists start disagreeing?
Yes. So the question is this point of plausibility being probability the point where frequentists start to disagree? And I think the answer is yes. So the reason why there is such a thing as a frequentist is that these rules are the same rules that proportions satisfy. So you can relate like the proportion of people who are taller than a certain height to the proportion of people that have heart disease or whatever, and the rules that relate those two things together are exactly the same mathematical rules, which is why it can sometimes be a bit confusing. Okay. So you can come up with all kinds of equations that are true using probability theory. So I'm going to just show you some of the most basic ones and the ones that it's good to remember. So the first one that I've written here is the sum rule, and that gives you, in general, the probability of A or B for any two propositions A or B, and you get it by adding the probabilities of A and B. And then if A and B aren't mutually exclusive, that is, they can both be true at the same time, then you have to subtract the probability that they're both true. So there's a version of the sum rule which is kind of more common, which is that if you assume that A and B are mutually exclusive, only one is true, then this third term goes away, and it just means that probability of something or something else is you just add the two separate probabilities. The second one here is the product rule. Probability of A and B, you can get that in two ways. You first give the probability of A and then times probability of B given A, or you can do it the other way around, equals the probability of B times A given B. And if you take these two and divide the B onto the other side, that's Bayes' theorem. Okay. There's the way people use this, there's a kind of version of the product rule that is the most convenient for people using this in practice, and it looks like that, but I'll skip on to the next one, I think. If you have a problem and you can think of like 10 or 20 or a million different possible solutions to your problem that are all mutually exclusive, and call those H1, H2, H3 up to Hn, then you can calculate the probability of each of your possible answers, the probability of Hi given some new information D, which we think of as data, and that's proportional to the probability of Hi not given D times the probability of D given Hi divided by the probability of D. So this is one equation, but it's really a set of n equations that gives you the probability of all your n hypotheses. So the terminology for this is that this probability here is called the prior probability because it's the probability of one of your hypotheses not using the data that you're looking at now, which is D. This thing here is called the likelihood for obscure historical reasons. It's the probability that if you assumed that Hi is true and then wanted to work and then calculated the probability of observing what you actually observed, that's what the likelihood is. And then on the denominator you have the probability of D not given Hi. So that includes the sum over all the possible ways you could have observed that data. Okay. So I think if you were going to commit to memory, if you didn't know it already, one version of Bayes' rule, the kind of fundamental one, this is probably the one to do. So almost everything that we do that's Bayesian is just an application of this formula, really. And the way I teach this to undergrad stats students who have only done one course on data analysis is that we make up a nice little table with, we write our prior probabilities for all our different possibilities and then our likelihoods, and all we're doing is multiplying one column of numbers by another column and then dividing by the sum of the column. It's really quite simple. So the other day I noticed during the breakout on hierarchical models when Phil was writing some probability theory down, and then Hogg was saying you've made a mistake. I thought that might look kind of mysterious to a lot of people who aren't already familiar with this stuff. So I came up with some questions. And the first question on the exercise sheet, which is in the repository, is just getting you to look at some equations of probability theory and to identify where the sum rule was used, where the product rule was used, and where a kind of non-general assumption has been used, like something was mutually exclusive or something like that. And the second one is an example of using Bayes' rule in this form to get the posterior probabilities of some hypotheses. So I'll give you a few minutes, maybe 5 or 10 minutes, if you want to work on the questions, and if you have any questions for me, let me know.
I would like to remind those of you who have experience with Bayesian statistics to identify yourselves to the people at your table for potential questions.
Where are these? Where is this?
In the inference subdirectory of AstroHackWeek 2015, and it's called probabilityquestions.pdf. And I've also put up the first 2 questions on the front. Okay.
This is a pen and paper exercise.
So both of these they could be pen and paper exercises or just talking exercises, just looking and talking. There's no computing yet. Bonus points if I've made a mistake in any of the equations.
Where was this be called? 1 and 2?
Yeah. I hope they're not too easy or hard.
That's a fair.
Yeah.
Yeah. I know, like, if there's people interested in cosmology in the room,
Yeah.
we're talking about the denominator, like the evidence,
Yeah.
like in a really general sense.
Yeah.
That you can think about that as the probability of data given your model.
Yeah, given everything that was on the right-hand side.
Probability of
Yeah.
the model. So, like, when
Yeah.
you have given the data, that should be given the data, comma the model. Right?
Oh, right, of
And
course.
so,
Yeah.
like, on the bottom, and like, so if you zoom out, you can be like, okay, our model is lambda CDM, but like, what if we wanted to consider
Yeah.
modified gravities? And then you can actually do like probability of all those cosmologies.
Yeah, yeah.
So like, you can keep zooming out and zooming out.
Yeah, definitely. I think I'm
like
going to
that's
talk about that
useful.
tomorrow, but you're going to allude to it as well? Yeah.
This is like the easiest form where H can mean cosmological model, but it can also mean the proposition that a parameter takes a particular is in a particular very small range.
No,
Yeah.
like in general, this should be d comma m.
Yeah.
And
Oh,
this
yeah,
should
yeah.
be d comma m,
So,
or
Ye-
d given
Brendon-
m on the bottom, and probability of m.
So he's doing the shortcut of like everything depends on.
So yeah, he's
Yeah.
removing, like, yeah, you can't
Yeah,
list
I'm-
everything, right? But like, if you were being really general, you would have given
Given
comma
something,
m.
and yeah,
Yeah, and
absolutely.
then the kind of interesting thing is on the bottom, people think about that as a normalization factor, but if you're actually interested in like weighing up lambda CDM versus modified gravity, that's when that
Yeah,
factor would become important, because
It's a likelihood, right?
then
It's
you can think about likelihoods of different.
yeah. It's you could call it a marginal likelihood. Yeah.
We're going to go through this in excruciating
Okay, cool.
Okay.
Sounds good.
Cool.
and then this evening painful debate.
I don't know if you've seen that, like, this really interesting paper by guys from Oxford, like Tessa Baker.
I don't know. I don't
so
think so.
basically they zoom out and zoom out, and like if you keep doing that, so you have like the probability of the model given the universe of all, or like the space of all models, and then
Yeah.
they stopped it there, and then they were like, we don't know what this means anymore.
Yeah, there is a point. It's kind of like the wave function of the universe or something.
Exactly.
Yeah.
Once you keep zooming out and
No, but
zooming
maybe
Yeah.
you can add a little bit of this statistical theory being correct. So we have a method to stop that.
Here, Brendon, that A column
Sorry.
B is A and B.
Yeah, comma means
means
and.
Okay, good.
Yeah. What did you say about Knuth and Skilling?
Oh, I
didn't
just said
hear
that
it.
they were maximally unclear. It's supposed to be
Oh,
very good
okay.
paper from people who are very unclear.
Yeah.
Did you is it clear to people on the live stream that we're doing problems 1 and 2 from this document?
I think so. I said on the. I think they can still hear me through this. So yes, we're doing questions 1 and 2 on the document. If anyone's following along.
Where can I find the presentation?
It should be probabilityslides.pdf.
Great, thank you.
No worries.
And there should be
Anyone having trouble? Yeah. Yeah, no problem.
But on this, so I've never done any base theory, so this might be a very stupid question. But
Yeah.
So the probability of data,
Yeah.
wouldn't that always be 1 because your data is what you are using?
That is actually a really good question.
Okay.
This is the probability that your particular data had before you knew that you had it.
Okay.
So when you get a particular data set, it becomes 1.
Okay.
But what appears in this equation is what it was before that you knew that was the data set.
Okay.
Does that make sense?
What would make it? I mean, why would it be different before?
So say I'm going to obtain, I don't know, what's an easy example for you? I'm going to do a medical testing example, so it's the probability that someone has a disease given that they tested positive.
Okay.
Before you get the test result, you don't know that they tested positive. So there was a probability of testing positive that isn't 1.
Okay.
And that's the number that appears in the denominator there.
Okay.
And then once they do test positive and you know it, then it becomes 1.
Okay.
Does that make sense?
Yeah.
Yeah. Yeah, I haven't defined independence, but I think it appears in one of the questions, so apologies for that.
Yeah, good. Good. So it doesn't mean they're mutually exclusive, of course, but if they're mutually exclusive, they're
Any problems?
I think
right? So this is the product rule. And the assumption that A and B are independent, which means that the probability of A times
Probability of A and B. Which one?
Independence.
Independence is P of A and B is P of A.
they're not true.
Yeah.
Sorry, true isn't quite right. They're valid.
Yeah, that's independence, because then probability of B given A is just the probability of B. A doesn't tell you about B.
Remember that? Is this
Yeah.
fully dependent, which is the opposite?
So Dahlia is some restriction on the world that would make 1 true.
Yes, awesome.
And she's referring directly to your notes.
Okay.
It's a very useful way to go.
Cool. Are there any blatant errors in question 1?
I don't know. I've only I checked the first 3 are correct.
Okay.
I should make a version of this problem for my notes. You can refer to my notes here.
Yeah.
I realize we should collaborate and write some.
I'm writing a book.
You are writing a book. Okay.
Yeah. Do you want a draft? I've written a preface
I'd be very happy to read
so far. I've got like 3 pages of draft.
You're writing a book the same way that I'm writing a book?
Yeah.
The estimated time to complete my book on data analysis is something like when I'm 250, I think.
But you've already written several chapters. It's
But
good.
I'm covering the rate at which I'm writing chapters.
Yeah. Okay. How's everyone going? Need a few more minutes or happy to move on? Happy to move on? Okay, let's go.
Good, exactly. And then the question is that
Okay. So one of the most common uses of sorry. Do people want to go over the solutions right now? Okay. Okay. All right. So people would like to see the solutions now, or go over the questions together. So I'll just quickly do that. So the first question, we were just looking at these equations and seeing where was the sum rule used in these equations, where was the product rule used, and where was there an assumption that is not completely general used in one of these equations. So looking at the first one, we've got probability of A and B given C, and it's been written as the product of the probability of A given C times the probability of B given C. And the fact that we're calculating the probability of an AND using a product means that that's going to be an example of the product rule. The given C is in the right-hand side of all of the expressions, so we can kind of forget about it. That's like background information of this equation. And the one thing that is different about this from the more general product rule is that the fully general version would be probability of A times B given A. So A would appear on the right-hand side of this. But since A doesn't appear, the assumption that's been made here is that A and B are independent given C. So independence means that B doesn't tell you about A doesn't tell you about B, so probability of B given A is just the probability of B.
Right, it's very interesting that's independence conditioned on C.
Yes. So
independent, but independent conditioned on C, which is a very strange thing to think about.
So the comment was, yeah, that the probability of that A and B can be independent given C, but not given C or given something else, they might become dependent, which can seem mysterious. I claim that it's trivial. So, okay, here's my justification for it being trivial for people that know what joint probability distributions are. Okay, so if I have a joint probability distribution for two variables x and y and it's independent, it's going to look like maybe like a circular kind of distribution, x and y, and they're independent. If I then condition on the proposition that x and y have to be close to the diagonal, so I kill all the possibilities off the diagonal, then the distribution becomes correlated. And so given the proposition that restricts everything to here, they're not independent anymore. So, or I could make them, I could do the opposite thing. So I could start with a distribution that's kind of elliptical, that x and y are correlated. So then, x and y are not independent, but then I could condition on, I could make a region and get rid of all the stuff outside that region such that the distribution became independent again. So it's not as mysterious as it seems. The second equation, we've got the probability of A or B given C. Again, we've got given C on the right-hand side of everything, so we can ignore it and think of it as being in the background for the purposes of reading the equation. Probability of A or B is probability of A plus the probability of B. We're calculating the probability of an OR, and we're doing it by using addition, so that's the sum rule. And the sum rule works where you just add the two probabilities, you don't have to subtract anything. That only works when A and B are mutually exclusive. Now, I haven't ever thought about mutually exclusive, conditional mutual exclusivity. I need to think about that, whether they could be not mutually exclusive if you took away the given C.
Yeah, we could draw a Venn diagram.
Yeah. Okay. Third equation, we have probability of A and B given C and D. What's on the right-hand side? Is there anything that's on the right-hand side in all the terms? Yes, there's D's on the right-hand side of everything, so we can ignore the D's and think of that as being in the background of the whole expression. And we've got some products going on here, so this is probably the product rule, but we've got a division here, so it might be more simple to multiply this up to the left-hand side if we wanted to have two products. But what this is just Bayes' rule to calculate the posterior probability of the proposition A and B given new information C, and it's in the context of old information D. So the posterior probability of A and B given C is the prior probability, so without the given C, times the likelihood, probability of the data given the hypothesis, divided by the marginal likelihood, the probability of the data, which in this context is C. And the final equation, it's got a sum, so it's got to be the sum rule. I is in the background of everything, and this is what this is doing is calculating the probability of Z when you know the probability of Z conditional on a bunch of A's, and you know the probabilities of the A's. So this is, you sometimes see it in textbooks, it's called the total probability rule. It's really just a version of the sum rule. That if Z can be true in kind of n different ways, Z could come true through A1 being true, or through A2 being true, or through A3 being true, or so on. You can add all those if they're mutually exclusive. And actually this assumes that the AIs are all mutually exclusive. Okay. Yeah?
You just said that P of C given A and B.
This one?
9-3.
Yeah.
You said that was a likelihood.
Yeah.
But you'd be talking about probability distribution. So what's the difference?
At the moment, I'm not talking about probability distributions, just probabilities. So likelihood is the probability of it's that term in Bayes' rule, basically. By definition, the likelihood is the label for that term. Okay. Do you need it?
I think of it as a label for the probability for C.
Yes. Yeah. Okay. Yep. the AI need to be mutually exclusive. Do they need to be exhaustive? Yes, I think they do. Yeah. Yes. So this inside the sum here there's a product. So this is the probability of A, I, and Z given I. And yes, if you sum that over all the AIs to get it to equal that, they have to be exhaustive, which means that there's the sum of all the A's has to be 1. Yeah. In fact, no. In fact, Z is very dependent on AI in general. There's no Z has to be dependent on. Well, it doesn't have to be, but I'm confused at the moment. Sorry. Could you repeat the question?
That's the product.
Yeah. So inside the sum there's a product rule, and then there's a sum rule. Okay. Yes, it is. But marginalization is an example of the sum rule. Yeah. And requires a. Yeah.
You chop up your parameter into little bins and do all the bins.
Yes. Yeah. So for question 2, this was a much simpler question. Although we have almost the same equation 4 and equation 6 appearing there, I think they might be exactly the same. So the question is about the denominator of the kind of standard version of Bayes' rule, and to give an intuitive explanation of it. So why would the probability of the data be equal to this sum? I think I alluded to it about a minute ago, but it might not have been very clear. So if we want to know the probability of D, the probability of getting a certain data set is the usual interpretation. And we also have these n mutually exclusive hypotheses in play, these HIs, then there are n different ways through which D could come true. It could come through via via H1, in which case the probability of that is the probability of H1 times D given H1. Or it could come about through H2 or through H3 and through H4 all the way up to through Hn. So the terms inside the sums are the probabilities of these n different roots, and if the HIs are all mutually exclusive, which they are in this setup, then you can just add the probabilities to get the probability of D. Okay. How are we for time? 0 o'clock?
It's 9:42.
Cool, thanks. So in most applications, it's easiest to use Bayes' rule in that form with the probability of HI given D. And one of the most common applications of Bayesian inference is to a subject that is sometimes called parameter estimation, which is just the idea that we want to know the value of some quantity. If we want to know the value of a quantity, then we can just come up with some hypotheses about what that value might be, and those hypotheses are propositions. So if a quantity we don't know is called theta, then we might think it's possible that theta is 5, or that theta is 6, or that theta is 7, and they could become 3 mutually exclusive and maybe exhaustive hypotheses as well. The data that you get to to learn about parameters, the data is often either a single number or a set of numbers, or a very large set of numbers. Could be big data, but this is the opposite. This is small data. If the data is a number that you try and take into account, then you can convert that to a proposition just by saying that the data equaling what it actually equaled is the proposition that you now know is true, and you're going to use Bayes' rule and condition on that proposition. So you could get so if you have this setup, you would have the probability that theta equals 5 given the data, given that D equals 4, is the probability theta equals 5 times D equals 4 given theta equals 5, and so on. And you do that for theta being 5, 6, and 7. So I thought just to connect Bayes' rule to parameter estimation, I came up with a little example that was inspired by watching a reality TV show about airport security. I thought that would be a good exercise for us to do, to just do an example of Bayesian inference that is parameter estimation, but it's just got 3 possibilities for the value of the parameter. So I'll give you a few minutes to do that.
Brendon, are you thinking about probability theory all the time?
No. No, but I'm always on the lookout for new questions. So for those of you who might be teaching at some point in your future but aren't, coming up with new questions for assignments and exams and things all the time is really impossible. So you have to be on your guard. Like sometimes you're just watching a reality TV show and like, question idea, you need to write it down or make a mental note. Sorry? Evernote. I had a suggestion from Kelly. Evernote. Is that a software? Is it software or is it?
Yes. Okay,
so yeah, Evernote apparently is good software for. Nice.
Yeah, you can notebooks, you can tag your notes, you have different notebooks, you can share them with other Evernote users.
Cool. This sounds fun. So check out Evernote if you're having this problem. Cool.
One person in this room who might never carry a device, it's Brendon.
I'm always on a device.
Oh, you are?
Yeah. I'm just not using it for anything legitimate.
Brendon?
Yeah.
Just a reminder to repeat the question.
Yeah, sorry.
Or the live stream.
Yeah, sorry about that. So if you want to do this one in Python, actually, you can make a numpy array of 3 prior probabilities, a numpy array of 3 likelihoods, and then just multiply them and renormalize them and get the answer in about 20 seconds. Not runtime, 20 seconds of typing time.
Prior would have been that each toy has a 50% chance of containing drugs.
Independently?
Yeah.
So that would imply a binomial prior on eta. Yeah. Yeah. So what actually happened on the airport security show was that they didn't want to test them. They had to like drill them and drill the toys and pull them apart and destroy them. It was destructive, so they didn't want to have to do it to all of them. I think they ended up doing it to all of them, and I think there were drugs in all of them. But that's less interesting than imagining that they didn't have the drugs.
Videos, the police are always responsible and competent.
Well, the airport security TV show for Australia is particularly exciting because they're like...
That's what this one was. It was, yeah, border security. It's fun. There's a New Zealand one actually, and it's pretty cute, like what happens when people are coming to New Zealand. It's like, oh, I went on some crazy holiday and brought home this, I don't know, this turtle shell thing that someone made for me. It's always the most random stuff. It's never like serious big business. So it's possible.
I want to not do any calculations and say that you
So possibly the hardest part of this question is thinking about the likelihood.
Right? So the probability, we have to ask what's the probability for eta 1 and eta 2. The probability for eta 0 is weird. I mean eta 2 is 0. That's also that 0, 1, and 2 are all correct. one sense, yes. Because when the data are so sparse, you just know that you ruled out one possibility, then it all happens.
Yep.
Is it hat?
I don't remember. The easiest way to get the
two toys and the probability that one of them has. I mean, if every toy have a probability of half.
That's a different assumption, though. Yeah.
So.
Yes. So I'm using this here.
Yeah. So this is good. This is good, and you have a third one.
Which is 0.
It would be.
Can't be eta p of eta equals 2, given that one of them does not have drugs is 0. So the whole term gets.
Yeah, it gets 0 because this term there is 0.
Exactly. The likelihood is 0. You couldn't have got this data if n was 2.
Yeah.
Oh.
Yeah. So you can write down the same equation again. It just happens that the one term on the right hand side is 0.
So
equals 2 is 0.
The probability of this is 1 and this
0,
is 1.
1. And if these are equal,
they can't both be 1. They can't both be.
Oh,
I see.
The likelihood.
Right, the likelihood.
Okay,
yeah.
so what you do to get these is you imagine that you knew that there were no drugs, and you say, what's the probability that I would... you would observe.
Definitely 1.
Yeah.
Definitely 1. Now this is not definitely 1, right? Because if 8 equals 1 and you drilled through...
And you drilled through one of them, what would be the probability that it had no drugs?
Yeah, what's the probability that you would get these data if eta is 1?
Yeah.
See, that's the non-trivial moment in this problem.
Yes.
I want to say half, but no, I'm forgetting.
This one, those are all 1/3, so that we do know.
Again.
But that's about your prior. You can
these other ones, that's what I'm having trouble with evaluating these other ones, like the probability.
So forget about prior.
How are we going for time? Okay. Okay. So I'm going to go through the solution now to this problem. I'll just do it in Python, make life a bit easier for doing the mathematics. Sorry? You want more time? Oh, we'll wait about another minute.
The thing on the bottom, yeah. The way I always think about it, I mean, it's actually a conceptual difference between Brendon thinks of that thing as an actual that brings you back. So I think that is irrelevant normalization. It doesn't change anything. Well, for one thing,
Phil, did you still want more time?
Universe actually happened, right? So you think about the probability.
Okay, I think there's a division between people for whom this is old hat and people for whom it's not. Yeah.
Good. I think, Brendon, this problem is so good. I think probably it would be useful to work, like, get the audience to work through the solution on the board, like once people have gotten close.
Okay. Do you want? We've had a suggestion that that someone writes the solution on the board.
But I would say give people a few more minutes.
Okay, in a couple of minutes. That's a good idea. It means I don't have to do anything. Yeah.
Yeah. So are you writing down the time? Are you writing down the dates? Okay, good. So for each of the there's 3 eta. You should write down that prior in that data.
So I got 2/3 for no dress. Yeah.
given eta, right?
Okay.
So if eta is 0,
If eta is 0,
what's the probability
Yeah.
then
There's a pretty, I think it's essentially the same problem, but so there's a pretty famous brain teaser, which is like, you know, your neighbors have 2 children.
Yeah,
Do you know this
and
one?
you walk past the bedroom and you see that it looks like a girly bedroom or something.
You see one daughter.
Yeah.
So then what's the probability the other child is a girl?
Yeah, and it's like,
essentially the
and
same
it's,
question.
yeah.
Because the knee-jerk reaction is it's 50% it's a girl, right? But then because you have the data, you kill the possibility that there's 2 boys.
Yeah, and that leaves 3 possibilities.
Right.
Then. Yeah,
exactly.
instead of 2. Yeah.
Yeah.
Yeah. And there's a number of famous probability puzzles that seem really easy and lead to all sorts of debates. So there's one of my favorites is the Sleeping Beauty problem, which I don't remember it exactly, but it's a brain twister because it involves erasing memory. It's about like someone who takes a drug and then goes to sleep, and the experimental protocol is that they're going to be woken up either on Tuesday or on Tuesday and Wednesday, and you have to assign the person's probability upon waking up that it's Tuesday or Wednesday, and there's like whole articles on whether the answer is a half or a third. And you can probably, get a good summary there. Yeah. Sorry?
Saying that eta is exclusive, does that mean summation
Some of the probabilities is...
probably eta I is 1, or
yes.
P of eta, like given D is 1?
It means that both of those are true.
Both of them.
And this is how you get rid of the unknown constant on the denominator. Because you just need to divide. So whatever you get 1/6 and 1/3. You just need to divide by their sum so that they sum to 1 again.
Right.
And if
you don't have a good feeling of what P of D means.
So that would be if I asked you at the beginning of the problem, what's the probability that no drugs will be found in the first? So they're going to check one of the toys. What's the probability no drugs will be found? And there's 3 ways that can happen. That can happen through eta being 0, or through eta being 1, or through eta being 2. And those are all mutually exclusive, so you can add the probabilities. Does that make sense? I think when you're just starting out, it's easiest just to forget about the denominator and then just work out all the numerators, so the 3 numerators, and then divide by the sum of them to make them sum to 1 again. Yeah. Okay, do we have any volunteers wanting to have a go at the problem on the board? Perhaps someone for whom this is a new subject?
Can you do it on the board and we shout at you what's right?
Okay, good. Okay, so I'm now going to write on the board whatever people tell me to write, but with the constraint that it's a solution to the question.
Coding in Brewer.
Yeah. Yeah.
So you suggested that we write Bayes' rule 3 times.
Okay.
Right.
Yes. So what's they're gonna look like?
So P of eta given the data, P of eta equals 0 given the data.
Okay.
Is P of eta equals 0 times P of data given the eta. Times P of eta times P of the data given eta equals 0 over P of data. So you can just replace that P of eta equals 0 as 1/3. That's the prior.
Actually, let's hold here.
Yeah.
So
Okay.
this is now a moment where people should if people have that.
Okay, did everyone get that? Do we agree that it's true? Is it always true?
We get it in NumPy.
Has a
different formulation.
has a secret assumption crept in? I'm going to use the skilling notation that I referred to earlier. All of this is given the prior information that I wrote in the problem.
The things you write in that corner can't be read. Because there's
Yeah.
It's because lights shine on it, so we can't see it.
Given I.
I mean, this is an incredibly strong assumption because the story is idiotic. So that's conditioned on idiotic. You know, in the sense that there's no way that this would be anybody's model of the world.
Yeah.
And in this case, it's very clear because it's such a simple, dumb story.
Yeah.
But actually, it's true in every data analysis that's ever been done. You're always making assumptions which, if you step back, you realize are ridiculous.
Yes.
Like you're assuming that your noise is perfectly Gaussian and the data really come from a perfectly straight line or whatever. It's just ridiculous.
Yeah.
Assumptions. So you're always conditioning on completely idiotic and ridiculous assumptions, and that's true here, and it's true in every data analysis that's ever been done in history of mankind.
That's true. So for those who are listening online and didn't hear that, the point was that that the assumptions in my story are, you know, simplistic and you could question them in a million different ways, but that's also true of the assumptions in every data analysis that anyone's ever done. To some extent.
That I could stand for idiocy?
So yes, given I, conditional on I, could stand for idiocy instead of we usually think of it as prior information. Yeah. Okay. So this equation, I think it's true. Do you want to substitute in some numbers? So what's this term?
That's just 1/3.
Prior probability that eta equals 0 is 1/3, because I told you to use that. In practice, you'd have to come up with some judgment for yourself. What about this term? The likelihood.
That's just the number 1.
Does everyone agree? Why is that 1?
So I assume that eta equals 0, so it is known that there are no drugs in the universe in one toys. So that the probability that I achieve the result that I drilled into a box and I see no drugs is 100%.
Yeah.
It's not possible for there to be another outcome.
Yeah, I agree with that. So yes, if you assume that eta equals 0, there are no drugs in any of the toys, the probability that your drilling experiment would not reveal drugs, which is the observed data, is 100%. And what about the denominator?
So just leave P of Z just as is.
I agree.
We're just going to solve for that.
So we'll leave it later. Do it later.
It's a very simple argument that it's a half.
There's a section in Jane's where he's...
we calculated that at this table and we got a half. And then as soon as we got a half, I was like, wait a second. There must be a simple argument that it's a half. Of course, there is.
Yeah, but it's better to do it the mechanical way that generalizes, not the random flash of inspiration way that doesn't generalize. Okay, so this is one of our 3 Bayes rules. What's the next one? Somebody? Any?
The exact same thing again for n equals 1.
Yeah. Okay, and some numbers. The prior probability that eta equals 1 is 1/3. And what's this likelihood now? If eta equals 1, what's the probability that you choose one of them and drill and don't find drugs?
If you choose the twice random. Not the heavier one?
That's a good question. That's a very good question because it reveals that whenever you're doing these calculations, you always find new assumptions.
Yes, so the question was, did you choose the toy to drill into randomly? And I would claim that the word random is completely meaningless, and that the only reasonable definition of the word random is that I write a half on the board.
But imagine one of the toys is much lighter than its volume in cocaine.
Yeah.
The other toy is about the right weight. By the way, cocaine's density is just less than that of water. And at least in powder form. And, it's slightly different in crack form. So
yes.
You can see how there's an assumption.
So there is an assumption. The point was raised that one of the toys could have been a lot heavier or a lot bigger or somehow have been different from the others that would make this not half. I was assuming that when you read this question, you just think of randomness or symmetry. Really, is what you're looking for. And in the case of symmetry, that that there was nothing about the two toys that would have told you which one might have drugs, in that case, then you're going to get a half.
There's no additional data. So you imagine a security agent in a bomb disposal suit with a long drill that stands across distance.
Yeah.
And all they do is drill and look. So there's
Yeah.
no picking up and weighing. There's no additional measurement.
Yeah.
They cannot find way two identical toys.
Yeah, two identical toys, apart from the existence of drugs, which cannot be detected through any means apart from drilling. Yeah. Okay. So again, this is always up for debate, but I just wanted you to assume a half, and then we'll leave the denominator again. And for the final one, probability ED equals 2 is prior probability of that times the likelihood of that.
Well, just write 0.
Yep.
Why could we write 0?
So this is 1/3. Why does it become 0?
Well, I mean, you can just write 0 by inspection on the left-hand side. You don't need to do nothing.
Yeah, but
You can, but that's a flash of inspiration.
Why
Yeah.
that is true? So can we go through that or reasoning?
So if it's 0, that means that drugs exist in both toys, but when you drill, you found no drugs. So you are wrong, and that is 0.
That's true. But how do we get it into how does it eventually become 0? Obviously this has to be 0, right? So it's this likelihood of being 0 that kills the posterior and makes it 0 as well. And we have the denominator as well.
Well, yeah, if you assume that A equals 2, then all of the toys in the universe have drugs in them. And so what is the probability that you drill into a box and find a toy that has no drugs in it? It's 0%.
But you just stated a likelihood statement.
Yeah, you're right.
But earlier,
you
made an equally valid posterior statement, which was like, duh, there were drugs, so it can't be that Ada was 2. Which
Yes.
is posterior
Oh, no, but I think
see, there's a slight difference between the likelihood statement and the posterior statement.
The obvious thing, I think, is the likelihood, not the posterior. How is the posterior obvious? The likelihood is just what I said.
Yeah,
so
okay,
if
fine.
you assume it's 100, that all
Fine,
drugs.
it's not going to make any difference.
But I think I was wrong. I don't think it's true that you can say that the posterior is obvious. It's obvious because
But
it's the likelihood
you
that's
did
obvious.
say the left-hand side.
Oh, I did. I was totally wrong.
The other left-hand side.
Yeah.
Okay. So what do we do about this denominator?
Hang on.
Yeah.
Wait, I don't understand why you can't make the same statement on the left-hand side.
I think you can.
You can, yeah.
Okay.
Oh.
Data is 0, so that's right.
But yeah, I mean, just intuitively, it's obvious that
And
you're
a lot of
intuitively doing this equation.
Yeah, exactly.
a lot of the time we do.
I agree. You're intuitively doing that equation.
A lot of the time we do that. Like even in science, like if you get a kick-ass data set and just look at it and now I know the answer. You can sometimes just intuitively know the posterior, and hopefully that's the case. I mean, otherwise we wouldn't be reasoning at all. No.
Yeah, they do in the sense that the intuitively knowing the answer depends on some support requirements of these probability distributions.
Yeah.
So
I think what.
Yes, but if you're setting your problem such that your intuitive answer is exactly probably.
I think the point at which you're becoming irrational is if you intuitively know the answer when you get the data, yet what you would have said before you got the data is some set of plausibilities that is inconsistent with what you're now saying after you got the data. As long as you're self-consistent, and this is the kind of extreme end of subjective Bayesianism, is that like anything goes as long as you satisfy the rules of probability theory. Yeah. Okay. So what do we do about the denominator? Anyone got a good suggestion?
I have a suggestion.
Yeah.
The probabilities you've computed need to add up to 1.
That's true. Why do they need to add up to 1?
Because I think you've enumerated all the possible states of the world on the left.
That's
so
correct.
The probabilities have to add up to 1.
Yeah, so the probabilities have to add up to 1, and currently they don't because, well, actually we can write down the equation that asserts that they need to add up to 1, which is 1/3 plus 1/6 plus 0 over p of d equals 1. P of D equals 1/3 plus 1/6. Who can do fractions quickly? That's a half, right? Okay.
Intuitively obvious way that P of D is. Because the intuitively obvious reason that it's 1/2 is in the first case, if eta is 0, you never see drugs. If eta is 2, you always see drugs. So those are symmetric, and they were equally likely cases. And then the middle one, half of them have drugs, so half the time you see drugs, also symmetric. So in half of the possible worlds you'll see drugs, and in half of the possible worlds you won't see drugs. And so the P of data, whichever you had drilled, would have been a half. Whatever you've gotten in the drilling, your P of D.
So notice the confusingness of some of the statements that people tend to make when they're talking about probabilities. They say things like, if eta equals 2, then you always see drugs, which is a frequency statement. But all we're trying to do is reason about an individual case. There's no notion of always and never. And sometimes, even if people are being Bayesians, they mix in the language of frequencies and proportions, which is just something you need to be aware of when you're reading things. So now we can just get all the probabilities. So it's probability of eta being 0 is, given the data, is 1/3 divided by a half. That's 2/3, right?
We're going to need another middle schooler to divide it.
So it's going to be 2/3, 1/3, 0. So we've just shown mathematically that the absence of evidence is evidence of absence, because the probability distribution is now different. You mean mathematically or the intuition one? So we were using the constraint that these 3 posterior probabilities have to sum to 1.
And so was Hogg.
And so was Hogg. No, there's a symmetry in the problem that gives it to you as half as well. That's what I think what
but the
was
way
being
he
asserted.
explained it, he was enumerating possibilities, which is what we just did.
Exactly.
Yeah.
You could boil it down instead of, these are 3 possibilities. So
Yeah.
like this, when you sum all the possibilities, the probabilities always have to equal 1.
Yeah.
So let's say you just have 2 options, right? The probability of something happening is some p value.
Yeah.
And then you know that something is going to happen, so 1 minus p is the probability of p not happening.
Yeah.
Either p will happen or p will not happen.
Yeah.
Right?
Yeah.
Those are the only 2 options.
Yeah.
And they both have to sum to 1. So 1 minus p plus p.
Right. Yeah. So the comment was that if you have something and its negation, the probabilities have to add up to 1, which is another. Yeah.
But does that imply that P of D is always a half, no matter what the D is?
No.
No, not in
No.
general, but in this problem.
In this problem, yes.
In this problem and for this data. So if the data had been different.
No, if the data had been different, P of D would still be a half, because the sum of the P of Ds over the different Ds have to be 1.
Think about it as normalizing a histogram.
Yeah.
A histogram, you can think about all those bars, and then you can set, if you're doing plot.hist, you can set norms is equal to true.
Yeah.
That's exactly what it's doing.
Yeah.
Right? And those heights adjust.
So we had
PDF, if you draw a PDF, that PDF would then be normal.
yeah. So this thing needs to sum to 1. You just get the same kind of thing going on.
Exactly, but you wouldn't have the symmetry argument about P of D.
Yeah.
It would remove a symmetry argument from the problem.
That's true. So that led to a lot more discussion than I thought it would. And we still have more questions. Yeah.
I just know, what does it mean to assume a uniform prior? That just means you're not putting in any information.
So the question was, what does it mean to assume a uniform prior on a discrete problem like this? Does it mean you're not putting in any information? That's a topic of debate. Whenever it was when Laplace was around and he came up with this stuff first, he used uniform priors like this a lot, and he called it the principle of insufficient reason. It's basically like, well, there's these possibilities and I don't know which one it is, so obviously you have to assign uniform probabilities. And I think my opinion is that uniform prior probabilities are a kind of way of just saying I don't know, but it's a way of saying that my uncertainty has a symmetry. My uncertainty can't tell the difference between eta being 0, 1, or 2. Those are in some sense exchangeable with each other. And that's kind of similar. We had the same thing with the likelihood in that problem. We had to say what was the probability of the data given that eta was 1, so given that one of the two had drugs and the other one didn't. And to say that that was equal to a half is kind of saying that I have no information that would lead me to prefer one over the other as having the drugs. I think it's a topic of debate in general, though.
I just feel like if you increase the number of toys,
yeah.
Then at some point, like intuitively, I would feel like if someone's asking me, do you believe that no single toy in the whole world has, of all the thousands of toys there are, has drugs in it, or do I believe that every single toy in the whole wide world has drugs in it?
Yeah.
And both of those intuitively would be less likely
than some number in the middle. Yeah, yeah. So if you, yeah, I think in that situation you're using your knowledge about the world to put a prior that seems to make sense to you, which is often the best we can do. And I agree that uniform, if you generalize this problem to like eta being somewhere from 0 to 1,000,000, a uniform prior would be ridiculous, because one consequence of it would be that the probability of eta being 0 is now 1 over 1,000,000, which seems too small, and other things like that.
But the uniformness would mean that it was 1 in 1,000,000, 1 in 1,000,000, 1 in 1,000,000 for these three functions.
You can always make the problem more realistic and add in extra things.
I want to say something about the security agent being maximally paranoid or something like that.
Yeah.
They're forgetting the intrinsic rarity of drugs in toys, and instead
security theater, a probabilistic model for security theater. Yeah.
Okay, what's the time now? I think
Adam had a question.
Okay.
I just had a quick question about PFD. So
yeah.
In this case, we're able to sort of argue our way through it.
Yeah.
In practice,
with
actual astronomical data, you just renormalize.
Renormalizing is always the easiest way to do it. You don't have to reason it out. If you've got your priors and your likelihoods, P of D is the sum of the prior times likelihood. And I'll just very quickly do this calculation in IPython to show you the general procedure, really. Okay, so I'll just quickly do the same problem in IPython. I'll make a prior, just a numpy array with 3 numbers in it. Those 3 numbers add up to 1. Those are my 3 prior probabilities. And my 3 likelihoods, and we did have to think about these a bit, but once we thought about them, they weren't that difficult to get. So the 3 likelihoods were 1, 0.5, and 0. And to get the posterior, it's actually, all you do is you multiply prior times likelihood. Well, that almost gives you the posterior. It doesn't sum to 1. You just need to divide by its sum to make it sum to 1. So that's quite easy. And those are the final posterior probabilities. And it came out to a lot more significant figures than it should have. I don't know how that happened, but that's pretty cool. So anytime anyone is doing a Bayesian analysis, even they've got complicated PGMs and they're analyzing the latest data set or something, the fundamentals of what they're doing is just this. It's just that they've enumerated a greater set of possibilities that might make sense to think of them as an n-dimensional parameter space, but the basic process stays the same. All right, I had another example that was simple, but I'll just skip it because it's we're running out of time. So what we just did was an example of parameter estimation where there were 3 possibilities for the value of the unknown parameter eta. Could have been 0, 1, or 2. In general, the way people do Bayesian parameter estimation is you just write down the version of Bayes' rule that looks like this. And I've changed a lot of things, and this is a kind of very dodgy notation that we all use, which doesn't make very much sense. But the way you can read it is that the posterior distribution for theta given d is proportional to the prior distribution for theta times the likelihood, which is the probability of the data as a function of theta. And this is just what we did in the drugs example. If we think of the prior distribution as being the vector 1/3, 1/3, 1/3, the likelihood function as being the vector 1, 0.50, and the posterior distribution is our set of 3 probabilities that we got out at the end. Okay. So a kind of recipe for doing Bayesian parameter estimation: first you come up with a hypothesis space or a parameter space, and anything that you're doing in data analysis that involves fitting and optimizing some function in parameter space, you already have your parameter space there. So if you're already doing like minimizing chi-squared to fit a model to data, you already have this ingredient in the hypothesis space. If you want to go from just fitting a function to data in that way to doing a Bayesian version of it, you need to add something else, which is a prior distribution over your space. It's a probability distribution describing how plausible each of the possibilities is before taking into account the data, and that gets updated, becomes the posterior. The other thing you need is a sampling distribution, which is I distinguish from the likelihood a little bit, because there's kind of you have the same term in the equations, but I like to distinguish between what that term looks like when the data is not known and what it looks like when the data has been substituted in. So before the actual data set is known and you write down a probability distribution for the data set given the parameters, that's a probability distribution over a space of possible data sets. And you can think of it like that. So it has to be normalized over the space of possible data sets. And that describes knowledge about the fact that the data that you're getting has something to do with the parameters that you want to try and learn. And if that's not true, then nothing really can be done. When you take this term and you plug in the actual observed data set, then it's no longer a probability distribution over the data space. It just becomes a function of theta. And this is the distinction between sampling distribution and likelihood, is that likelihood is, by some authors, likelihood is reserved for only the latter thing, a function on the parameter space, because you've substituted in the observed data. It's no longer a probability distribution over D. Okay. So the version of Bayes' rule that you use for parameter estimation just looks like this. It seems the same as the original, or one of the older versions of Bayes' rule, but all these P's are now probability distributions, and they can also be continuous densities. So you can think of this as like a super vectorized version, a vectorized way of writing down Bayes' rule 1,000,000 times if you've got 1,000,000 elements in your parameter space, or infinitely many times if you have a continuous parameter space. Then each of these, this will be a function of theta, a function of d, and d and theta, and a function of d, and a function of d and theta. The denominator then in a continuous problem becomes an integral instead of a sum, and there's two names for that. There's the marginal likelihood and the evidence, and that has another use apart from the normalizing constant, which I think we'll get to today and tomorrow. You can use it for model selection. Evidence tends to be the physics word, physicist word, and marginal likelihood is the statistician word. But you'll see both of them around, and some people just use both or whatever. There's a new term that has come out of the NYU group, which is the FML, fully marginalized likelihood, and it also describes how difficult it can be to compute in practical problems sometimes. Okay. So if you have a parameter space that you're currently and you're currently doing a fitting problem by finding the best fit in parameter space, the definition of best fit usually corresponds to what in statistics is called maximum likelihood. So I've just got a little picture here of a one-dimensional parameter space for some quantity theta that could be between 0 and 100. And the prior distribution for theta I've just said is this blue curve, and the likelihood function is this dotted curve that should be cyan, but we're having some color issues with the screen. It looks kind of gray there. And this likelihood function, if you go to the peak of it and say that's my value of theta that I'm going to estimate, and that's the best fit, that's the maximum likelihood, but it's not necessarily the most plausible value of the parameters, because the most plausible value of the parameters would be one where the posterior probability is high. And this posterior distribution is the product of the prior times the likelihood renormalized to make it a probability distribution. So to convert any maximum likelihood fitting code into a Bayesian code, you take your likelihood, which is the thing you're already optimizing, you multiply it by a prior, and then you replace the optimization procedure with some other algorithm which will instead quantify all properties of this distribution, because this distribution describes all your uncertainty about the value of theta. And the most convenient set of methods for doing that is Markov chain Monte Carlo, which I think Phil is going to introduce soon. Okay. I do have some one-dimensional parameter estimation exercises on the sheet, but in the last few minutes, I think I will just talk a little bit about priors, and people can do the question sheet in the coffee break if they want to, or any time later today. Feel free to ask me any questions. So we've already had a lot of discussion about how to choose prior distributions or prior probabilities in smaller problems, and there are kind of three main ways people do it. Number 3 is the most common, and that is that you use tradition, conventional spherical cow type things. So in a lot of papers you'll see that the prior distribution for an unknown parameter is chosen to be uniform in some fairly wide range. It could also sometimes be uniform for the log of the parameter, and I'll have a short discussion about why that's a good idea soon. And other assumptions like a Gaussian distribution for the noise in the data, which is largely just a convenience thing. If you want to be formal about it, there's two ways to be formal about it. One way is sometimes called objective Bayes, where they try and find symmetries or definitions of what it means to be ignorant that uniquely give you a prior distribution. And I think those are interesting things to think about, but for practical data analysis, you don't really need to go there. The other approach, which some statisticians use, is called subjective Bayes, and that's sometimes it's based on the kind of client. What's the opposite of a client? So you've got a statistician, and the statistician is a consultant for a client who's an expert in some field, and the statistician's job is to do the Bayesian analysis based on the prior beliefs of the expert in the field. So they will conduct an interview with the expert and try and probe how confident they are in various propositions and assign a prior that agrees with that. And I have a hack pitched for that, but I've never actually done it formally, so a lot of the hack would be just reading the literature on how to do that well. Yep?
Are you going to be having any discussion later today or tomorrow about calculating evidence and priors?
Yeah. So the question is there going to be discussion on calculating the evidence? So this normalizing constant, which has applications beyond just normalizing the posterior. The answer is yes. So tomorrow I'm going to do a presentation on nested sampling, which is... Oh, and after coffee today there's some discussion of that with Phil as well.
So
yep.
In your list, where would you put, in your list of priors...
that one?
Where would you put physical Bayes? where a theoretical physicist derives a prior PDF for parameters of the model they're interested in.
Okay, so the question was where would physicist Bayes or something come in, which is that a theorist has a theory from which they produce a prior distribution for some quantity. I think that I would probably call that closer to objective Bayes because they've used principles to get to it. But it would be objective Bayes applied to a conditional probability in the model. So the theory would usually give you the probability distribution for something conditional on the theory that the theorist was working with. But I think in spirit it's closer to objective Bayes because it's derived from something. And I think that's the difference. So objective Bayes is being derived from something explicitly. That doesn't mean it's right or good or anything, it just means it's derived. And subjective Bayes is often just, well, I feel like that's implausible, which sounds not very scientific, but actually will often give you better results than objective Bayes.
I bring it up because objective Bayes sounds like the goal is to have an uninformative prior, but I guess that's not always the case.
I don't think so always. There's a lot of connections between objective Bayes and uninformativeness, and that a lot of the research is along those lines, but I don't think for me that's not the defining feature of it. If it's derived from some explicit principles or something.
But here you would still have to place a prior on whatever method you have used in order to get to your...
Exactly, that's what Brendon means by it being a conditional distribution. Right.
Yeah, so at some point it can be that in your when you're writing down all your assumptions, that what you write down for your sampling distribution for the data might be really well justified, but what you write down for the prior distribution for the parameters is just pulled out of the air, and some combination of these is often what happens.
In that instance, like you couldn't just leave the prior parameters in this theory, but you also have to penalize that by multiplying by the parameters.
Yeah, the probability of the theory would have to come in, otherwise you couldn't do anything, unless you wanted to do all your inference conditional on that theory. Yeah.
Which is what we do all the time, right? Basically all of our abstracts, all the conclusions in our abstract are conditional on the set of assumptions we made.
Yes, yeah.
And then we spend the whole paper explaining what our assumptions are.
Yes, yeah.
This might be getting covered tomorrow or something, I don't know, but what if you really have no idea at all what your prior should be?
Yeah.
How would you go about it? Like, would you just kind of pick, like, uniform or Gaussian something?
So the question is, what do you do if you have no idea at all what prior to pick, and can you just pick something and then cross your fingers? And I think you're always free to do that. And the question you're answering when you do that is, this is the conclusion I get from this prior, and that can be helpful. Even if you think you're completely ignorant of something, there are usually some constraints that you can bring in. So, for example, I don't know, the strength of the magnetic field in this room or something, even though I don't know anything about geomagnetism, I could probably put a constraint on, like an upper limit on it, because otherwise we'd all be dead, and obviously it's not going to be zero. So there's something there. And another thing that you can do is you can imagine what information, you can imagine hypothetical information that you could imagine getting which would lead you to know what prior to assign. So if someone said, I have a magnetic field measurer over there, and it's accurate to within 10%, and they told me what their measurement was, then I would have a good idea of how to assign my prior. So then I can write down my prior conditional on the result of this hypothetical measurement, but then I need to put in a prior for what the hypothetical measurement is going to be. But that leads into the idea of hierarchical models. So that's what hierarchical models are.
But let's say we didn't have the measurement, you could just have a uniform prior that just has the min and the max. And uniform probability for that range.
You can do that. It's the most common thing. Yeah. There can be unintended consequences to that, which I just want to discuss for about 2 minutes, and then maybe we'll take the coffee break. So there's another thing you can do is if you just assert a prior, rather than just doing your calculation and then publishing it, a good thing to do is to check your prior for unintended consequences, and sometimes these can be a bit surprising when you're not used to them. So for one example, imagine that we wanted to know the mass of a galaxy in solar masses, and we're denoting that mass by theta because that's a symbol that makes sense. Makes sense to me. Theta is just the unknown parameter. So if you were ignorant of the mass of a galaxy in solar masses, you know something about the universe, so you know that it's going to be more than zero solar masses and less than 10 to the 15, say. So you could assign a uniform prior between 0 and 10 to the 15, and just in case you haven't seen it before, this is a really fast notation that statisticians use to write down probability distribution assumptions. You write down the name of the parameter, then twiddles, then the name of the distribution, and then the parameters of the distribution. So in the uniform, everyone knows that it's the min and the max. And so if you just write this down, you don't have to write down the density, the equation for the density. It's a really fast way to communicate. So one consequence of this prior, you can derive arbitrary consequences of it. You can get the probability that the mass is in any interval just by integrating the density function. So two consequences of this are that the probability that the mass is greater than 10 to the 12 solar masses is 99.9%, and the probability it's greater than 10 to the 14 solar masses is 90%. So we were trying to describe ignorance by putting a really wide uniform prior, but it turned out that this implies confidence about something that maybe we shouldn't be so confident about. So there's a common alternative for situations like this, especially in astronomy. This is really useful because in astronomy a lot of the time we have to put the error bars in the exponent, and this is a prior that's really useful for putting error bars in the exponent. It's to apply the uniform distribution not to the quantity, not to a positive quantity that you want to measure, but to the log of a quantity. And a reason why this is good is it treats then differences in the exponent of equal length have the same prior probability. So if we replace the uniform prior with the uniform prior for log theta, so we write log theta is uniform maybe from 5 to 15, then we can calculate some consequences of that by integrating it within any interval of possibilities, and we can get that the probability it's greater than 10 to the 14 is 0.1, or greater than or equal to 10 to the 12 is 0.3, and 0.1, 0.3, these are much more moderate numbers. They're a lot less sure of themselves. And the best property of this prior is that the probability of being between 10 to the 10 and 10 to the 11 is the same as 10 to the 11, 10 to the 12, same as 10 to the 12 and 10 to the 13, and so on. So this is a very good kind of default choice for if you don't know what prior to choose, but you know that your quantity is positive, and in a sense the error bars are in the exponent.
So this is like better in the case that we know we have the idea that the prior depends like order of magnitude.
Yeah. If the uncertainty is over
0 and 10.
If the uncertainty is over orders of magnitude of a positive quantity, this is pretty much the description of that. And if you want a version that's kind of like this but a bit more informative, so it's over orders of magnitude, but only a couple of orders of magnitude, not like 10 or 20. Another alternative that you can use to do that is log normal. So just thinking of the parameter in the log in that case makes sense. So the prior density for this turns out to be that if you assign a uniform prior to the log of the density, then the density for the parameter itself is proportional to 1 over the value of the variable. So in many problems, you can actually just derive the posterior analytically by writing down the equation for the likelihood and plugging that in for the prior, and that's what one of the exercises on the exercise sheet has you do. When it comes to likelihoods, one of the most common things that you'll see for assumptions for the sampling distribution or probability distribution for a data set is that most data sets aren't a single number, they're a collection of numbers. For example, all the pixels in an image or all the measurements in a time series. And a really common assumption is that the probability distribution for the full data set, which I've written as a vector here, given the parameters, can be factorized into a product of one term for each of the data points of a common assumed probability distribution here, which I've called F. And this assumption is called independent and identically distributed. So independence has come in because I'm just doing the product, and each term in the product doesn't refer to any of the other data points, it just refers to one of them. And identically distributed because the distribution of each of the data points is the same. It's just this F, whatever it is. So IID, Gaussian noise, is probably the most common assumption that you see in data analysis in astronomy. So if you manage to do the rest of my exercises, you'll hopefully get the hang of one-dimensional parameter estimation, and of course most problems have more than one unknown parameter in them. So the probability distribution describing your knowledge, the posterior, is a joint distribution over possibly a high-dimensional space. And high-dimensional spaces and what probability distributions look like in high-dimensional spaces is not that easy to intuitively understand, and also computationally you can't just do this like grid of possibilities that you can do in one dimension. So the main techniques to deal with that are Markov chain Monte Carlo. Just to give a brief motivation for Markov chain Monte Carlo, if you have a high dimensional posterior distribution like this, and it's for two parameters A and B, but you mostly care about A, you just want to look at the posterior distribution for A. The procedure to get that is to integrate over all values of B, and you get a one-dimensional density like that. Now this integral, you could sometimes do it analytically, or in 2 dimensions or 3, you could do it numerically, if you 2 or 3 dimensional grid and sum over some of the dimensions. But in high dimensions, it's really annoying. You can't do it anymore. So in high dimensions, instead, what you do is you generate a lot of points from this distribution using MCMC or something like that. And then the advantage of doing that is that the procedure of marginalization becomes trivial. So even in really high dimensions, if you want to just look at the probability distribution for A, all you have to do is just make a histogram of all the A values of your points and just ignore the B values. And that's a lot easier than doing a high dimensional integration. You can also use the sum rule to see how prediction works in Bayesian inference. It comes out fairly naturally. So if you wanted to predict some new data, D new, from some data that you already have, D, then you can write this out using the sum rule, then use the product rule here, and then there's an independence assumption in going to the third line. But what this tells you to do is that if you want to get the posterior distribution for your new data, you imagine that you knew the value of the unknown parameters, and you kind of go through all the possibilities that might be, and you get your answer conditional on that. So you assume you know the true theta, get all your answers for all the different values of theta, and then you make a mixture of all those distributions, which is what that integral is doing. And that kind of smears out the distribution to take into account the uncertainty from not knowing the value of theta. So the last exercise question is getting you to do this on a one-dimensional example. And that's the end of my presentation. Thanks.